Welcome to the introductory video about optical reflection. It's chapter 35, and after our discussion in class, remember to go back and do the readings, and it's sections 0 through 10. One of the aspects of reflection I wanted you to realize is that reflection happens at the surface of an interface. So where we change from one optical medium to another, that's called an interface. And when light hits an interface, if it does not pass into the new medium, it reflects.
Some materials, like glass, let a lot of light pass through them and reflect only a little. Other materials, like polished metals, reflect most of the light that strikes them and let only a little through. In glass and other materials that don't reflect much light, electrons can vibrate only over small atomic distances. In metals, some electrons, the so-called conduction electrons, can vibrate over distances much larger than the size of an atom. When light strikes glass head-on with zero angle of incidence, about 4% is reflected and 96% transmitted. On a polished metal surface, it can be the other way around, with more than 90% reflected. When light is incident on a rough or granular surface, it's reflected in many directions. This is called diffuse reflection. If the smoothness of the surface is such that the distances between successive surface elevations are less than about 1/8 the wavelength of light, there is very little diffuse reflection and the surface is said to be polished. The wire mesh dish is very rough for light waves and so is hardly mirror-like. But for long wavelength radio waves, it is polished and therefore an excellent reflector.
A concept that we need to use is called a light ray. Now we know that light is a wave, and there are many aspects of it that are explained through this wave nature. Even this reflection is actually a property of a wave. For clarity and for ease of use and drawing and modeling, rather than using a wave to represent this electromagnetic wave, this light, we're going to use a ray to represent the path that the electromagnetic wave follows. So a ray is a straight line used to represent a path of light. It does have a directionality in that it originates someplace and terminates another place, and that is how we represent it. So it's not a vector in that it has a specific length, but it's a ray in that it continues on forever, but in a specific direction. All right, let's look at the law of reflection very quickly. Here is some things from Hewitt.
The interesting thing, though, is that whether a lot is reflected or only a little, and no matter what the reflecting surface is made of, the light obeys the same simple law of reflection if the surface is smooth. The law of reflection is the angle of incidence equals the angle of reflection. The blue arrow represents a light ray. Instead of measuring the angles of incident and reflected rays from the reflecting surface, it's customary to measure angles from a line perpendicular to the plane of the reflecting surface. This imaginary line is called the normal. The incident ray, the normal, and the reflected ray all lie in the same plane. Such reflection from a smooth surface is called specular reflection. Mirrors produce excellent specular reflections.
All right, so for our law of reflection, we have that the angle of incidence equals the angle of reflection. If we look at our equation sheet, it's this equation right here. Angle of incidence equals angle of reflection. And as you saw in the video, those are always measured to the normal. That normal line being perpendicular. If you think back and remember back, we discussed normal lines when we talked about forces, and we had normal forces always being perpendicular to the surface. All right, so let's take a minute to look at how do we see an object in a plane mirror. I've got a plane mirror here in the middle of my space, And on the left hand side I have an object that's giving off light. These are these little rays coming from it. And we all know, or we've seen, we've experienced, that the image of this is going to be on the other side of the mirror. And as we go closer to the mirror, our image gets closer. If we go further away, we dance around, it's always going to stay in that other side of the mirror. And I'd like to explain to you why. We know this is a light ray, this is a ray box, so we have some light rays coming out here, that when those light rays strike the mirror, they do not go through it. This is one of the critical parts of a mirror, is that the light doesn't go through it. So the rays of light from this light box do not penetrate the mirror. They get cut off directly, and actually what's happening is they're getting reflected by the mirror. So right now I'm shooting them in at the normal being perpendicular to the mirror. As we see, this blue line is also normal to the mirror. If I send them in not normal to the mirror, I see them reflecting off of the mirror in a different path than they went in. And that's the angle of reflection equaling the angle of incidence. The angle of incidence being measured to the normal and the angle of reflection being measured otherwise. I'm going to cut it down to one ray, and then we can bring it down here to a normal line and see. Oops, I'm going to have to change my angle a little bit because I can't drop it right there. That may be enough. Yes. So I can see that the ray of light actually comes in, hits the mirror, and comes out. And if I was to measure this angle, the angle of incidence, versus the angle of reflection, I would see that those are exactly the same. So that's easy. That's with a single ray. We can see that it bounces off of the mirror, and we have that law of reflection. The difference between what is known as a virtual image and a real image. A real image is where light actually crosses or actually meets. Anything projected on a screen is producing a real image. If you think about our projector in class that projects on the smartboard or projects on the whiteboard, that is producing a real image. A virtual image is where light appears to come from, but does not really come from there. Your brain can only handle the fact that rays of light travel in a single constant direction. So when light enters our eye, our brain traces that light back to where it appears to originate from by a straight line path. If that straight line path leads it to where it originated from, that's a real image. If that straight line path does not come from there, but interacts with a mirror or something else, then that is called a virtual image. The next topic I'd like to discuss is ray diagrams with planar mirrors. So here is a short demonstration that I built up about ray diagrams. What happens when we have an object is, if you remember, or in case you don't know, an object has lots of rays. So I'm gonna show you. It's got rays from the middle, it's got rays from the top, and it's got rays from the bottom. So it's got all of these different rays of light. In fact, there's infinite numbers of rays of light coming from that object, and they're all individually hitting the mirror, bouncing off of it, and then, but how does them bouncing off it, create this virtual image over here? Well, let's close this down a little bit. Let me get that open again. Let's go to ray settings, and we'll bring this down to here. We'll go 0, we'll go down to 1 here, and we'll go down to 0 here. And so what's happening here is we've got one ray of light. We got one ray of light coming from the top, hitting the mirror, and reflecting off the mirror. So how does this ray of light coming off and hitting the mirror, how does that get traced back to forming this virtual image. To look at that, we're going to look at the eye up here and pretend that this is the eye that you're looking at it with. And let's pick one ray of light coming from the top to the eye. And you can see here that ray of light leaves the top of the object, hits the mirror, it reflects across the normal with the same angle, and comes back to the eye. Now here's the tricky part. The reason it forms a virtual image, our eye thinks that this ray of light traveled in a straight line. Well, for it to travel in a straight line, it would have to originate back here beyond the mirror. And therefore, where our eye perceives these rays coming from is where it places the virtual image, because our brain only knows one way to interpret the image, that the rays of light traveled in a straight line from the object to our eye. If that actually happens, if our eye actually gets rays of light from the real object, that's fine. That's how we know where things are. But if those rays of light are interrupted, their path by like a mirror, our brain only knows one way to handle that, is that that light came from a straight line. So when we're doing a ray diagram here, we don't really worry as much about the eye, but we start looking at, okay, where do rays from similar points, where do they cross? Where do they come from? And we'll do that in lab. Alrighty. We have a couple other topics to discuss. One of them is how tall should a full-length mirror be? And here is an explanation of the thoughts that are going into that.
Consider Blinky Bill, who wishes to view his full-length image in a mirror. We'll see that his distance from the mirror is the same as the distance of his image, which to him looks like his twin. Both Blinky Bill and his twin are of the same size, with the mirror directly between them. This brings up an interesting question. What is the minimum height for the mirror to show Blinky Bill's full-height image? If you're not familiar with the answer, get ready for a surprise. First of all, Blinky Bill is in an illuminated room, so zillions of light rays reflect from all points on his body. We'll focus our attention only on rays reflecting from his shoes, then from his hat. Of the zillions of rays reflecting from his shoes, we'll consider only one, the green ray that gets to the mirror and then reflects to his eye. This ray meets the mirror halfway between Blinky's eye and his feet. Rays in other directions would reach below, above, or off to the side of his eyes. Let's look at light from his hat that reaches the mirror. Of the many possibilities, only this ray will reflect from the mirror to Blinky's eye. What does Blinky Bill see? The lower ray extends to his twin's feet. To Blinky Bill, light from his twin's feet is what reaches his eye. Likewise with light from his hat, which appears to come from Blinky Bill's twin. If Blinky Bill is 6 feet tall, how tall is the part of the mirror that provides a full-height image? Can you see it's 3 feet? Another thing about mirrors. Some of your friends might ask why a mirror reverses left and right. But does a mirror really reverse left and right? Here's my sister Marjorie in front of a mirror. As you can see, her left-right axis is no more reversed than her up and down axis. The axis that is reversed is front-back. And note another thing. The color of her clothing in the mirror is the same. Evidence that reflection doesn't change the frequency of light.
Alrighty. The next topic, and this is the one actually that we're going to spend a little more time on. I mean, we'll do a lab on planar mirrors, but talking about spherical mirrors here. Mirrors that are either convex or concave. And I thought this video from UCLA did a great job of explaining those and some of their uses.
Convex and concave mirrors can be just as useful as lenses, solving many of the same problems. Let me show you how they work. Convex mirrors reflect light outward, resulting in an image that will always appear upright and smaller. You may have seen these kind of mirrors in a fun house. Here, the vertical is undistorted, making the horizontal view skinnier. Concave mirrors reflect light inward and can be used to focus that light. The focused light can be used to generate heat. A concave mirror can also be used to project an image. Notice that this image is always upside down, and because it's formed in the real world, we call it a real image. When the object is within the focal point of the mirror, the image in the mirror appears upright and magnified. Perhaps one of the most important uses of a concave mirror is the reflecting telescope. Not only do these telescopes provide high magnification, but they also solve a major problem that all lenses have. When light passes through a lens, there will always be a dispersion of colors, the prism effect. This can cause a blurriness which is hard to correct for. It is called chromatic aberration. Mirrors don't have this problem. Therefore, these days, most of the best telescopes are using concave mirrors rather than lenses. These include Caltech's Palomar telescope, the Keck telescope in Hawaii, and the famous Hubble telescope orbiting the Earth in outer space.
So, one of the things that goes with the spherical mirrors is what's called the focal length. And the focal length is half the radius of curvature. The radius of curvature being the radius of the circle that would make the mirror. In our equation sheet, we have that equation right here, that the focal length is half the radius of curvature. We also have some other equations here about mirrors and optics, about distance to image, distance to object, and magnification. These will be explained and gone over in some activities that we do in class. Getting in some vocab, though, is the last thing that I wanted to do in this video. So, some of the vocab that we use is center of curvature, which is also the radius. That would be the center of the sphere that made that curve, made the mirror. The focal point, as we just discussed, is the point that is halfway between the center of curvature and the mirror. So the focal length is half of the radius of curvature. The line here connecting this is called the principal axis, and sometimes it's also called the optical axis. That is this axis of symmetry through the center. When we have an object, the object is going to be a certain distance from the mirror, called the distance to the object. It's going to have a certain height of the object. The image will be a certain distance from the mirror and will have a certain height. So you've got a lot of vocab here. Center, radius, center of curvature, focal point, focal length, height of object, height of image, distance object, distance image, and either principal or optical axis. I think through some use that we do in class, you will come to understand and be able to use those terms correctly. So I will see you in class.